to Everest, 29,000 feet. And we want to find the gravitational force that exists between the girl and the Earth. So almost all of these are a picture of some sort where you have object one and an object two.
Mhm.
The mass, we'll say mass one, mass two. Mass two is the 52.25 kilograms, the girl. Okay. I am not sure why your instructor is giving you the weight of the girl at sea level. Let me look into that. Yeah, not sure that. So we need the mass of the Earth. The mass of the Earth is it's a known value. It's 5.976 times 10 to the 24th. And this is probably the hardest part, is the distance. So like this is exaggerated, but there's the radius of the Earth plus the distance of this mountain, the height of the mountain. Because she's not on the surface of the Earth anymore. She's taller, to say the least. I guess. So it's the radius of the Earth. The radius of the Earth is 6.378 times 10 to the 6th meters. And this height, this distance here that we have to add to it, we need to figure that out. So that it's 29,000 feet. But then we have to convert feet to meters.
Okay.
So your instructor gave you a conversion here. I don't know if you would have that on the exam, but you would get.
Yeah, we do.
Okay. And you don't have to go out to so many decimal places. I know it probably feels like, oh, I got to go out and do a bunch of them. You really just got to go out to one, not even one decimal place, because these numbers are so large. Okay. Now I should have started with the equation. The force of gravity between two objects is G m1 times m2 over the distance squared. The distance in this problem is the radius of the Earth plus the height of the mountain. So that's why you go to all this trouble. So the distance is 6.378 times 10 to the 6th plus 8,841 meters squared. And then in the numerator, you have the G, which is 6.67 times 10 to the minus 11. Then you have the mass of both. So the mass of the girl, or the mass of the Earth, is 5.976 times 10 to the 24th. Mass of the girl is 52.25. And you go. So what is your comfort with entering this into the calculator? I remember doing this with you maybe a week ago.
I can do it. I think that sometimes it's just where I struggle with the problems in general. It's just like setting it up into the, like plugging everything in.
Okay. All right. So let's, it's up to you if you want to do the calculation or not. That's where I was going, but I understand your concern, and we should do more problems to help with that.
Okay.
I really have no idea why your instructor keeps giving you the masses of them, the weight at sea level. Okay, can we move on to number 2?
Mhm.
All right, number 2. So to your point, to your concern, like what is really important about these is setting up a picture. And
Mhm.
the picture needs to be only good enough that you understand what is happening. So we have an astronaut who is in orbit around the Earth. So again, not to scale, but here's the astronaut, here's the Earth, and they're going around it. Is that clear? Somewhat clear?
Mhm.
So this formula we've been talking about, G m1 m2 over d squared, you have to decide which one is 1 and which one is 2. Now you could use a convention like the bigger one is m1, the smaller one is m2. It doesn't really matter. It really doesn't. So which one do you want to call m1, the astronaut or the Earth?
The astronaut.
So the astronaut is m1 and the Earth is m2. Okay. So we got some of those values, 84, and then the mass of the Earth is whatever it is from the previous problem. It's 5.976 times 10 to the 24th. Okay. Now, oh, I see what they're doing. I'm sorry. This one is different. Forgive me. Now I see this one is different. Okay. How much will an 84 kilogram astronaut weigh while in orbit around Earth? An altitude of, the astronaut weighs 823.2 newtons at sea level. I see why they're doing it this way. Okay, let's see if I can help you out here. So the force of gravity is what we're trying to determine here.
Mhm.
And so we need to know, you almost always find FG first. That's what we did in the previous problem. We want to find FG. So do we have enough to find it? We know the mass. We know the mass. G is given. G is given. Do we know the distance? Now it's the center. It's between the center of the two objects. So it's the like orbit plus the radius of the Earth.
Mhm.
So how far above the Earth is it?
237 miles.
Right. And we need to like convert that to meters because we're working meters. So 237 miles times 1 mile is 1.61 kilometers. And in 1 kilometer, there is 1,000 meters. So we want to get that number there, whatever that is.
Okay.
So it's pretty big here. It's 381,570 meters. Okay, so we need the radius of the Earth. The radius of the Earth from the previous problem is 6.378 times 10 to the 6th. There. Meters. So you're trying to find the force of gravity. That's not the answer to this question, but that's the first part of it. So you have to put the numbers into this equation. 8.67 times 10 to the minus 11. Mass 1 is 84. Mass 2 is this giant number, the 5.976 times 10 to the 24th over the distance is the radius of the Earth, the 6.378 times 10 to the 6th plus 81,570 all squared. So will you, if you have a calculator, will you do this calculation? And I will as well, so we can see if we get a similar number.
Okay.
So G. And I think we talked about last time, you can just use E and then the exponent.
Mhm.
Okay, so I got 1,043.
That's what I got too.
Great. And the units of that is meters per second squared, because it's like an acceleration. So now,
Mhm.
like, if we go back to what the question is actually asking, it'd say, how much will an 84 kilogram weigh? Your weight is mass times gravity. And this FG is that. And I think sometimes that's unclear. You're finding gravity. When we say G, we mean the force of gravity. So
Mhm.
the weight is 84 and the gravity is 1,043 there. And I have no idea if that's reasonable or not. Like I don't know if that force is actually what it is out there.
Wait, where did you get the 8.67 times 10 to the negative 11?
That's G. That's the force of that's the gravitational constant. It's always that.
Oh, okay.
It's always that. It never, never changes. Okay, can we move to 3? Or no, I guess it's the next one. We probably should have done that other one first. It would have been more clear now that I see what's going on here. Okay, determine the gravitational force between a 141 kilogram man and a 70 kilogram woman that are standing 2.25 meters apart. So let's draw a picture. Here's the man. And usually circles are good. Here's the woman. Okay, the man has a mass 1 is 141. The woman mass 2 of 70. And they are a certain distance apart.
Mhm.
What is this asking for?
Um, the gravitational force.
It's asking for FG. FG equals G M1 M2 over D squared. Do you have those values?
Yes.
You do. So that's where you put those into the given equation. So try setting that up. And see if if you can get the result here. And if these are clear, we can do some more like the other type. So it's 6.67 times 10 to the minus 11, 141 times 70 over 2.25 squared.
Okay, that's what I got too.
Okay, great. Do you want us to do this calculation, or do you want us to move on to the next question?
We can move on.
Okay. All right. Okay, an astronaut visiting a planet far away steps on a scale and finds his weight to be 650 newtons. The astronaut has a mass of 85 kilograms and he stands 5.2 times 10 to the 6 meters away from the center of the planet. So again, it's kind of another like one of those. Here's a planet. We don't know how big the planet is, but we know that the person is this far away. 5.2 times 10 to the 6 meters away. Okay, now what are we trying to find? We're trying to find the mass of the planet. So the mass of the planet is unknown. We'll call that M1. The mass of the person, do we know that value? 85.
Yes.
Okay. Now, do we have enough information to do this? So the only equation we have is the following. We have FG equals G M1 M2 over D squared. So what information do we have here? Do we know G? Yes. Do we know M1? No, we don't know that. That's what we're trying to find here. Okay. We know M2 and we know D. Usually we're finding F of G. Do you agree with that?
Yeah.
Okay. So that's a problem. Like we have two unknowns here. So let's go back and look one more time. So the information we use that, we have not used that yet, the 650 newtons. So your weight is your mass times the force of gravity. Okay. So the force of gravity that's the same as this value down here. The weight is 650. The mass is 84, so we can find the force of gravity, or 85, sorry, 85. So there's really only two equations. There's this one, weight equals FG, and FG equals this whole thing over here. So your force of gravity is 650 over 85. So okay. That's 7.65. Okay, so now that's the value that goes back into this equation. So that 7.65 is the force of gravity. G is the 6.67 times 10 to the minus 11. The mass of the planet we don't know. We know the mass of the person is 85. And we know the distance between them is 5.2 times 10 to the 6 meters.
Okay.
Okay, so you're solving for M1 here. So there's two approaches you could take here. One is to like actually multiply and divide, like multiply, divide, square. And so, or you can kind of rearrange things. Which do you think
Mhm.
you would do on a test or quiz?
Rearrange.
Okay, so let's actually rearrange this equation. So like you know FG, you know G, and you know M2, and you know D squared. So like you're solving for M1, solve for M1. So the first thing you might do is multiply both sides by D squared. Okay, like that.
Mhm.
So you get D squared times FG equals G M1 M2. Now M1 is what we're trying to find. So we divide both sides by the other variables, G and M2, G and M2. And see how they cancel?
Mhm.
So your M1 is now D squared times the force of gravity over G times M2. So now you just
Okay.
substitute those numbers in. Your D is the 5.2 times 10 to the 6th meters squared. Your force of gravity was the number we found, 7.65. G is the 8.67 times 10 to the minus 11. The mass of the person is 85. So when you do all this, you get 5.75 times 10 to the 12, or 5e to the 12.
Okay.
So there's another problem here for us to look at, number 3. And then you can maybe tell me which one, is making sense, not making sense. Do some of the other. Okay, at high noon, the sun appears directly over your head. If the sun pulls on you with a gravitational force of 0.4393 newtons, find the distance from you to the center of the sun. So try to draw a picture of this scenario on your own. See if you can come up with like what it is that's going on here. So let's say this is the Earth,
Mhm.
and the sun is much bigger. So if you care about that, I mean, the relative, sizes are maybe important. Who knows? Okay. Now you are standing on the sun or on the earth.
Mm-hmm.
But what happens is like you are part of the earth. So like your mass adds to the earth. And it's negligible, but we'll do that here as well. So M1 is the mass of the earth plus you. And the mass of the earth is whatever it is. Let me go look here. These numbers don't mean anything. That's why they're hard to remember. So it's 5. Hey, Julia, you able to see my screen?
Yes. I don't know how I got disconnected. That was weird.
Did you miss any part of this question that we need to review?
Um, I think I disconnected right before you wrote the equation.
Okay. So the mass of the earth here, or M1, it's the mass of the earth plus you, and we're just trying to find that number for the mass of the earth. It's 5.976 times 10 to the 24th. That's a number you need to know, plus 74.5. Okay, so that's your M1. The mass of the sun is given, it's 1.989 times 10 to the 30th.
Okay.
What is this number here? What is this 0.4393? What quantity does that represent?
What quantity?
Yeah,
FG?
FG, right? It's the variable FG. FG is 0.4393. And you have two equations really to choose from. FG equals G M1 M2 over D squared.
Mm-hmm.
What are they asking you to solve for in this question?
The distance from
The
you to the
distance.
center of the sun.
So D in this equation. So you have to solve this equation, solve for D. Okay, so is that something you're comfortable doing? Like, do you see I have to get D out of the bottom?
Yeah.
So you want to cross multiply here, butterfly thing. D squared times FG equals G M1 times M2. Okay. So to get D by itself, you divide both sides by FG. And D squared equals G M1 M2 over FG. And then you take the square root of both sides. And this only works
Okay.
because you have all of those quantities. You already know each of the values. Like G is 8.67 times 10 to the minus 11. What is M1? We said M1 is the mass of the earth plus you. It's this number over here. It's this 5.976 times 10 to the 24th plus 74.5. And then mass 2 is the mass of the sun. Mass of the sun is 1.989 times 10 to the 30, all over the force of gravity. And that's the number that they gave you, the 0.4393 square root of all that. So are you comfortable putting this in your calculator? Or, would you like us to do it together? Check it.
If we could check it, that'd be good.
All right. I will work on that now. So I get 4.84 times 10 to the 22nd.
Okay, that's what I got too.
Excellent. Okay, so we've done 5 problems. Which one or ones is maybe unclear?
The one that we did in the beginning where it talks about sea level.
Okay. Yeah. So these are written kind of oddly, but let's look at another one here. So okay, trying to figure out how to like do this. So just check a number here. 23.2 or okay. All right, so okay, so the like the whole construct here is that like you're in this like fictitious world, like where there's only like 2 things that exist. So Julia is right here,
Mm-hmm.
and there's a giant planet right here. Okay, we're gonna make some of these numbers simple. Forgive me, I don't know if this is true or not, but we're gonna go 40 kilograms for you, and the mass of this planet over here is it's 10 to the 25th kilograms.
Okay.
Okay, and it's got a radius of this planet is 10 to the 9th meters. We're just making nice numbers up. Okay, and
Okay.
you are in orbit. You are in orbit 10,000 meters above the planet. Okay.
Mm-hmm.
So from this given information, what can you calculate? Can you calculate the force of gravity? Do you know G?
Yes.
Yes, it's always the same. Do you know the mass of the person 1 over here called Julia?
Yes.
Do you know the mass of the other thing?
Yes.
Do you know the distance between the 2?
10,000 meters?
Well, that's to the surface, but you have to go right to the center.
Oh.
You have the radius of the planet, so that like right to the center is 10 to the 9th meters.
Oh, okay.
So you add them up.
Yeah.
So it's the distance squared. Yes, you have that. So go ahead and put these numbers into your equation and see if you get. So tell me what you end up, or I'll write the answer here as well. Did you get 3.5 times 10 to the minus 2? Or maybe it was 0.035 on your calculator.
Yes.
Okay. So if you got that number now, okay, your weight is m times g. It's always m times g. Now on Earth, what is g? What is g always on Earth?
6.67 times 10 to the negative 11.
Nope, 9.8, 9.8.
Oh, okay.
This big G is like G in the galaxy. Little g is on Earth. Right,
Oh,
remember you did a bunch
9.8.
of problems. It's like 40 times 9.8 or 10 times 9.8, right?
Yeah.
We talked at length at one point about how your mass does not change. Okay. What is your mass in this problem? It's 40. Your FG, though, is this value that you just calculated. So you have to find the force of gravity between the two objects.
Yeah.
And once you do that, that becomes your G value.
Oh, okay.
We're going to simplify this in the next example, but I want you to go through the calculation one more time. So notice your mass is always the same, but your weight could change based on where you are.
Okay.
Okay, so let me give you let me try to clarify this. Okay, so let's say you're here and something else is here. Okay, and you have a mass of 40 kilograms. There's a force of gravity in this universe, this system. You do all the calculations, you find the force of gravity is 1.5. Okay, you do that calculation, G m1 m2 over d2 squared. Okay, what is your weight? Your weight is your mass times G, but your G here is this number. So your mass is 40, but G is 1.5.
Okay.
Because you calculated, like you did all the calculations. Like I gave you the mass of this planet, I gave you the radius of the planet, I told you how far away you are, you did all the calculations, it gets down to 1.5. Well, your weight is mass times gravity. Gravity is whatever the force of gravity is in this problem.
Okay.
So it ends up being 60 newtons. I still don't think this is clear. Maybe you're tired. I don't know. Tell me I'm wrong, or what can I do to help here make this better?
Can we do one more example, please?
Of course. So again, like let's say you and someone else are in some place, and we do all the calculations. You have a mass. Someone has a mass of 20 kilograms. The other person has a mass of 80 kilograms. Okay, and you do all the calculations, and you find the force of gravity is 6. It's exactly 6 or whatever. Maybe we'll go 6.2. It doesn't matter. Okay.
Okay.
Weight is always mass times gravity, but gravity is Fg. So weight is really mass times the force of gravity.
Okay.
Okay, so what is the weight of thing 1 over here? It's 20 times 6.2. What is the weight of this other one? It's 80 times 6.2. So and that's it. I mean, that's it. So we're skipping the step of like finding the actual force of gravity, But once you have the force of gravity, you take your weight and you multiply it.
Okay.
It maybe if you've I'm just gonna throw out there, like if you want to maybe try and verbalize what is still unclear, I'll try my best to give a better explanation if it is.
I don't think it's unclear anymore.
Okay, that's good. That's good. There are only two equations here. There really are. G m1 m2 over d squared, and sometimes weight equals mg. Sometimes, and this g is really this g. This little g is really that g.
Okay.
All right, we have a few minutes left if you would like to use it. Where would you like to go next? What would you like to do at this point?
Could we do one more practice problem?
Sure. Okay, so let me come up with this, fictitious planet scenario again. So planet 1 has a mass of 10 to the 18th kilograms. Planet 2 has a mass of 10 to the 20th kilograms. This one has a radius of 10 to the 8th. This one has a radius of 10 to the 7th, and they are a distance. They're currently a distance of 10 to the 4th apart. What is the force of gravity?
Okay.
So take a minute here, minute or two, and then I'll jump in and see if I can help. How are you doing on this?
I'm just entering it into my calculator.
All right. So the main one, I'll just do that first, is the distance between the two is not, it's not this 10 to the 4th. It's the sum of these three, because you got this radius, the distance between them, and then this radius here. So it's like 10 to the 7th plus 10 to the 4th plus 10 to the 8th. So I got 7.2 times 10 to the 11th when I did this calculation.
That's what I got too.
Great. Okay. So now let's say I wanted the weight. The weight is mass times gravity, right? This number right here is your G. Okay, so let's say I wanted the weight of planet 1. It would be m1 times the force of gravity. M1 is 10 to the 18th. And the force of gravity is 7.2 times 10 to the 11th. So you'd multiply those together to get the weight.
Okay.
Okay, well, I really hope this helped. You did great going 2 hours. So I certainly appreciate your scheduling, and I'll see you next time.
Okay. Thank you for helping me.
You're welcome. Have a great night. Bye now.
Bye.